Chapter 6. So now we're going to be looking at inequalities, specifically comparing sides and angles in one triangle and comparing sides and angles in two triangles. So we got a couple different theorems. 6.4 starts on page 219 in your textbook. This is where these theorems are. So we first have the side inequality theorem. That's what I've named it. In your textbook, it's just theorem 6.2, but that's generic and boring. So we're calling this the side inequality theorem. It says if one side of a triangle is longer than a second side, then the angle opposite the first side is larger than the angle opposite the second side. In other words, larger angles are across from larger sides. Smaller angles are across from smaller sides. So just as like a general statement here, you have side RT, right, is across from angle S. You have side RS is across from angle T. And if I tell you something along the lines of, because right now it's the side theorem, if I told you that if the measure of RT is greater than the measure of RS, then we're going to know, since RT is across from angle S, that's going to imply that angle S is greater than the measure of angle T. So then the measure of angle S is greater than the measure of angle T. So again, larger angles across from larger sides, etc. The angle inequality theorem is just that same idea, just flipped around. So it says if one angle of a triangle is larger than a second angle, then the side opposite the first angle is longer than the side opposite the second angle. So same exact idea, flipped around. Your larger angles are going to be across from your larger sides. So you can almost just take that first statement and flip it around. If I tell you that the measure of angle S is greater than the measure of angle T, then we're going to know that the measure of segment RT is greater than the measure of segment RS. Those theorems are normally pretty intuitive. That makes sense, right? Larger angles across from larger sides, etc. Okay. Then we have the triangle inequality theorem. And it says that the sum of the lengths of any two sides of a triangle is greater than the length of a third side. What this theorem is basically telling us, or what it's making a rule for, is if you have a triangle, only specific side lengths will actually work. You can't just take any three measurements and make a triangle out of like three segments with those measurements. The measurements have to meet certain criteria. And that criteria is that the sum of any two lengths, or the sum of any two sides, must be greater than the other one. So if you pick any two sides, their sum has to be more than the third. So for example, if I told you that the measure of RS was 7 and the measure of RT is 10 and the measure of TS is 15, that would work. You could form a triangle with those units because 5 plus 10, that's more than 15, right? 10 plus 15, more than 7, etc. But if you had a situation maybe where the side lengths were 7, 10, and what won't work? 20 or 845, like Tyler said, that won't work. Because if you take 7 plus 10, that's not greater than 20. Okay, so it has to meet that criteria. Are there any questions about those three theorems? Pretty straightforward. Okay. Now we have two corollaries. The first one says that the perpendicular segment from a point to a line is the shortest segment from the point to the line. In other words, the shortest distance between a point and a line is the perpendicular measurement. We've talked about that before. And then Same idea, but with a plane. The perpendicular segment from a point to a plane is the shortest segment from the point to the plane. Again, shortest distance is always the perpendicular segment. We've talked about that. That just kind of comes up again here. So let's take a look at a few things. It says that the base of an isosceles triangle has a length of 12. What can you say about the length of a leg? So the base of an isosceles triangle has a length of 12. What can you say about the length of a leg? So this is kind of having you imply some information here. And it wants you to imply information about the side length, right? So think about what this would look like. You're going to have an isosceles triangle. And this is not drawn to scale, but it has a base of 12, right? And if it's isosceles, what do we know about the two sides or the two legs? They're congruent, right? The two legs are congruent. So think about the theorems we just talked about. What can we imply about the length of the leg? Is there something that's going to have to be true about it if the base is 12? Very good. It has to absolutely be greater than 6. Because think, if this was 6 and 6, 6 plus 6 is not greater than 12, right? If it was anything less than that, it also wouldn't work. So at minimum, it's going to have to be greater than 6. Perfect. That's exactly what we wanted to see. So what can you say about the length of a leg? Its length must be greater than 6. Good. Two sides of a parallelogram have lengths of 10 and 12. Or I don't think that, no, that is meant to say parallelogram. What can you say about the length of a leg? So what it wants you to do here is draw a parallelogram, but that parallelogram is going to have to have, I'm sorry, can you say about the length? Oh, that's why that doesn't make sense. This should say, what can you say about the length of the diagonals? So what happens when I type things too late at night? So two sides of a parallelogram have lengths of 10 and 12. What can you say about the lengths of the diagonals? Okay, so we got a parallelogram with a diagonal. Two sides of the parallelogram have lengths of 10 and 12. What can you say about the lengths of the diagonals? It doesn't really specify which sides, though, does it? So what I would probably say is if you have a diagonal, isn't that cutting your shape into two triangles? So let's say let's say this side here was 10 and this side was 12, but it wouldn't really matter, right? Because if the left is 10, the right is 10, right? If the top is 12, the bottom's 12. What can we imply about the length of that diagonal? Thinking about our triangle inequality theorems. Okay, it would have to be less than 22. Is there anything it has to be more than? I agree with the less than 22 here. Let's put that. Yeah. It has to be less than 22, and it also has to be more than 2. If you prefer, you can always write it as that they have to be between 22 and 2. An easy way to figure that out is if you're given two measurements and you have to figure out the possibilities for the third, add and subtract. Right, and then that's like your two limits. So like if you take 10 and 12, that's 22, right? So that's your greatest limit. It has to be less than that. and then just subtract. So you could do that with any set of numbers. If you had 5 and 15, right, it would have to be between 5 plus 15 is 20, so it has to be less than 20. Or if it's 5 and 15 and you subtract, it has to be greater than 10. Okay? So last one of these, two sides of a triangle have lengths of 15 and 20. The length of the third leg can be any number between what? So what do we get if you just use that little trick I taught you? Yep, add and subtract. You add to get your upper limit, subtract to get your lower limit. So it must be between 5 and 35, or 35 and 5. Doesn't matter there. Okay. Questions about how any of that works? Okay. 6-5 then, that starts on page 228 in your textbook. So for this is going to look kind of familiar. It should, except now we're dealing with inequalities. We have the side angle side inequality theorem. And that says if two sides of one triangle are congruent to two sides of another triangle. So let's say I told you that segment AB was congruent to DE and segment AC was congruent to DF. Oh, actually, wait, so that it corresponds better with your textbook. I'm going to make it the bottom side in case you guys look at that for an example. Okay, so we got two sides of one triangle are congruent to two sides of another triangle, but the included angle of the first is larger than the included angle of the second. So then what this is saying is that the measure of angle B is greater than the measure of angle E. Then the third side of the first triangle is longer than the third side of the second triangle. Very similar idea to what we did up at the top of this, where larger angles are across from larger sides and vice versa. Here, if you have two triangles where two of the sets of sides are congruent, here if angle B is larger than angle E, then the measure of AC must be greater than the measure of DF, because bigger angles make bigger sides. So we could just say if the measure of angle B is greater than the measure of angle E, then the measure of AC is greater than the measure of DF. And that does only work if you have triangles with two sets of congruent sides. And it must be the included angle. Then we can do something similar, but using the sides to show that one angle is larger than the other. So the side inequality theorem says if two sides of one triangle are congruent to two sides of another triangle, so same idea here, if segment AB is congruent to ED and BC is congruent to EF, but the third side of the first is longer than the third side of the second. So if I told you that segment AC was larger than segment DF, then the included angle of the first is larger than the included angle of the second. So same idea, flipped around. If we know that the measure of segment AC is greater than the measure of segment DF, then we're going to be able to imply that the measure of angle B is greater than the measure of angle D. Or E, I'm sorry. Measure of angle B is greater than the measure of angle E. Any questions about how that works? It tends to be a theorem where it's a long theorem. It kind of sounds complex, but then once you look at it in a diagram, it should be reasonably straightforward. We good? Okay. All right, so really we just have a couple examples. I wanted to throw a proof in there. So that way we could look at that together. It was going to be on your homework, but I put it on the notes instead. So you're welcome. So for this, it's just asking, what can you deduce? Name the theorem that supports your answer. So here we have two triangles. It is telling us that TA has a measure of n, TC has a measure of n. We have a 31-degree angle and a 32-degree angle. Now for this is like those theorems we just talked about. N and n means we have a set of congruent sides. We also have a shared side in the middle with TB. So those are our two sets of congruent sides. So all this is asking us is to take these angle measurements and use it to deduce something about the sides. What do you think we could deduce about two of the side measurements based on the information we have here? Any ideas? Someone said so. Oh, Braden, what's up? What do you think? Exactly, yeah. And how you would just write an inequality for that is really the easiest way to do it. I would simply say that the measure of BC is larger than the measure of AB. And then if it asked you which theorem, is this the side angle side inequality theorem or the side 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 inequality theorem? Yep, side angle side, because we used our angle to imply that our sides were larger. Good. So then you would say side angle side inequality is how I'm going to abbreviate that. Then if you take a look at B, we have our two triangles with two congruent sides because we have 10 and 10. So there's one set. And then we have our shared side in the middle. There's our second set. What this one's asking us for is, since it's giving us side lengths and not angle measurements, it wants us to deduce something about our angle measurements. So based on this diagram, any ideas of what we can deduce about our angle measurements? Yeah, precisely. All it wants you to do is take a look at what it's across from, right? Angle 1 is across from 6, 2 is across from 5, so we can deduce that the measure of angle 1 is greater than the measure of angle 2. And would that be side angle side or side 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 inequality theorem? Yep, side 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 inequality. Good. So that's the gist with a lot of that. Sometimes your pictures might get a little more complicated, right? You might have to use one angle to figure out another angle measurement and then go from there. But that's the general concept. So let's take a look at a proof. I even put the weird three-dimensional one on here for you guys so that it wasn't on your homework. I was feeling generous. So we have that plane P bisects segment XZ at Y, and the measure of YZ is greater than the measure of YX, I'm sorry, WX. WX is greater than the measure of I can't read. The measure of WZ is greater than the measure of WX. We're going to prove that plane XZ, that segment XZ is not perpendicular to plane P. So we want to prove that this is not perpendicular. Where did my book go? We want to prove that this is not perpendicular. So obviously, you can always throw your given in there first, but I would like to take a look at our picture before we do too much with filling in the actual proof. So does anyone see? Think about the theorems we just discussed. Any ideas of some information we could use here and maybe tie in our side angle side or side 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 inequality theorems? That's precisely what we need to do. Very good. Awesome. So, yeah, so let's go ahead. Let's throw our given in there. So we are going to say that plane P bisects segment XZ at Y. So think about what that's going to tell you as we go through and write this. We got a bisector there. We're going to have some congruent segments down at the bottom, right? And we know that the measure of WZ is greater than the measure of WX. Okay, no problem, Tyler. Sorry if my handwriting is really terrible today. My tablet has been extra glitchy. Okay. So we have that plane P bisects segment XZ at Y, and that WZ is greater than WX. So Peyton says we're going to need to use the side inequality theorem. We got to get there though, right? I marked that these are congruent, but we don't have that quite yet in our proof. So where should I go next from here? How can I use my definitions? Remember, if you have a vocab word, use it. How can we use our vocab? Oh, Braden? Do you think you know? I thought you had like the little, I don't know if you had that up from before still. Nothing, you just had your little hand raise symbol still up. I think you just had it up. You just had it up from, yeah. Anyone have an idea? I see a vocab word. How can we use the vocab word? Yeah, we need to use the bisector. What does a segment bisector give us though? A midpoint. So we're going to say that Y is the midpoint here. So we're going to say that Y is the midpoint of segment XZ. That is the definition of a segment bisector. What do I do from there? Come on, guys. This one's this part's basic. This should be this part. Yep. Say that segment XY is congruent to segment YZ. That's the definition of a midpoint. So now we have one set of congruent sides. Where's our other set of congruent sides? Because we need two sets of sides here. Braden? Yep, that's our shared side there. So we're going to have that segment WY is congruent to segment WY. There's our reflexive property. Good. So now I have my two sets of congruent sides. I don't really need anything else, do I? I actually think I have an extra line here. Because I think one way to do it is to put your given in two different places. But if I already know that WZ is greater than XZ, won't I be able to imply here that angle WYZ is greater than angle WYX? I'm going to be able to imply that, right? So that's what we're going to say next. We are going to say that the measure of angle WYZ is greater than the measure of angle WYX, and that is our side inequality theorem. And then if one angle is greater than the other, why is that going to imply that it's not perpendicular? What do we have to have if they're perpendicular? Congruent adjacent angles. We don't have congruent adjacent angles, do we? So there's a few different things I would accept here. The way the solution guide does this one is it actually doesn't even put your proof. I always like you guys to put your proof. It's how you really know that you're done, you're where you're supposed to be. So there's a few different things that I could maybe accept here. Segment XZ is not perpendicular to plane R. And couldn't you almost use some of the things you learned in an indirect proof here? I mean, this isn't an indirect proof, but aren't we basically like it's negating a theorem basically, right? If we said that these were perpendicular, right, that would contradict one of our theorems. It would either contradict the definition of perpendicular lines. It would also contradict our congruent adjacent angles theorem, right? So there's a few different ways you can do that. But I would probably just give one of those, whichever one you feel more comfortable with, whichever one you like better. You could say definition of perpendicular lines, or you could say perpendicular lines form congruent adjacent angles. I would accept either one of those as an appropriate reason. Again, it's saying it's not, but that's how you would know. So I'm going to say, because here it's specifically talking about congruent segments, or I'm sorry, congruent to a plane. So we also have our theorem, a line perpendicular to a plane. Do you guys remember when we talked about that? I think that was either earlier this quarter or first quarter. Line perpendicular to a plane theorem. That's technically also what it could contradict. So I'm going to put that. Line perpendicular to a plane. Oh, is it technically a definition, not a theorem? Definition of a line perpendicular to a plane. Okay, so that's what a lot of those proofs are going to be about, seeing what sides would have to be greater, what angles would have to be greater, and you are going to have to use potentially some of your old vocab, midpoint, segment, bisectors, etc. I tried to keep it pretty short so that you guys had plenty of time to start your homework, which I need to type in. Any questions before I tell you guys what that's going to be? No? Okay.